solutions to the review sheet we were doing this week about the exponent laws. All right, we'll start with question 1 here, which pertains to this idea that we can use exponent laws to solve an exponent problem, but we can also use this principle of expansion, and either one should get to the same answer. And this is kind of a powerful idea because it allows us to use two different methods. If we're confused about one, we can always check using another. I think I'm going to bring the camera in a little bit to make my work seem a little bigger here. And I'll just focus that. All right, so let's get it started with 1a. So we're going to expand each power in this question. So I'll start with a to the power 4, or pardon me, a to the exponent 4. That means a times a times a times a. And that's being multiplied by a cubed, which means a times a times a, which is being multiplied by a raised to an exponent 5, which means a times a times a times a times a. So you can start to see why we developed laws to sum up these patterns, because it's kind of tedious, as you'll probably find, writing out all these variables. Okay, and then we could say, well, can I write that more simply? Well, how many a's are there? There's 3, 6, 9, there's 12. So I can actually express that as a to the power, to the exponent 12. I can also have simply used exponent laws to do this. A to the power 4 times a cubed times a to the power 5. And the property we can use is the rule that when you multiply powers, you add their exponents. So this is really a to the power 4 plus 3 plus 5, which simplifies to a to the power of 12. Same answer, two different ways. One you'll probably think is a little bit less tedious than the other. All right, let's move on to 2. So I could express b raised to an exponent 10 as, well, that really means b times 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 b. 1, 2, 3, 4, 5, 10. Okay. That's raised all over b raised to an exponent 8. B times b times b times b times b times b times b. I hate my life, times b. Okay, and then we can say, okay, we know this principle of canceling factors that are on the top and the bottom of a fraction. What we're really doing when we say canceling is dividing the top and bottom by that factor. So I can divide the top and bottom by b, cross those guys out. But sometimes we abbreviate that thought process and we can just cross these suckers out. And this always works provided there's no addition or subtraction on the top and bottom of a fraction. Once there is, we need to think a little bit more carefully about what we're doing here. And then we have 2 b's left over, b times b, all over 1, which is the same thing as b times b, which I could simplify to be b squared. I could also use my exponent laws for this. B to the power of 10 over b to the power of 8. That's a division, so I can express that as a subtraction of the two powers, subtraction of the two exponents. 10 to take away 8, which is b to the power of 2. Okay, lastly, we could expand this power to a power here. So what I think I'll do is I'll start with the outside power. I'll say I can, you know what? As a good habit, it's usually helpful to start on the inside. So I'm going to say I can write that as x times x times x, that's x cubed, as cubed. Which means I can say that's x times x times x, all multiplied by x times x times x. That's all multiplied by x times x times x. Okay, and I can express that really as x to the power of, there are 9 of them there, x to the power of 9. Now, the more simple way to do this is to use the exponent law. This is really the essence of mathematics. There is some principle, and we're looking to sum up the rule so we can do it in a simpler process. And so an exponent law is a great example of that. So it's x to the power of 3. We use the multiplication principle here. So it would be x to the power of 3 times 3, which gives us x to the power 9. Okay. And on the back, we've got some practice questions that allow us to just make sure we really understand the principle of these exponent laws. So we'll just run through these pretty quickly. Okay, this is the addition principle when you say, I could simplify this as 2 to the power of 4 plus 6, which is 2 to the power of 10. And we could just leave it like that. I could say this is 3 to the power of 12, take away 9, which is 3 to the power of 3. Now, I happen to know that's 27. And I happen to know this one, if I remember my binary, is 1024? Question mark? That's actually one I want to double check in my calculator. 2 raised to the power of 10. How big is that? It is 1024. Okay, cool. All right, and then we have 5 to the power of 4 raised to the power of 6. I'm just going to circle these. Those are the answers we really want. Okay, and that's a multiplication principle. So it's 5 to the power of 4 times 6, which is another way of saying 5 to the power of 24. Now, I know that's going to be a tremendously big number. Something like a septillion, 5 septillion, or something like that. Actually, maybe it's a little smaller. And it's really, really big. I wouldn't want to write out all those zeros. So I'm going to leave it like that. Okay, same principle here. Okay, we've got several things going on here. We've got a multiplication. We've also got some exponent steps here. And so I really advise us to use BEDMAS if we're ever unsure about which thing to do first. It can often help us to just be a little efficient with our steps here. It will work if we don't tend to use BEDMAS often, but in my experience, it's a good framework for approaching a problem if we're not sure which step to do first. Okay, so the first thing we'll do is we will do the exponent step here, which says I'm going to apply the exponents inside these brackets, which means we're going to multiply these together. It gives us a to the power of 2 times 3, which is a to the power of 6. And that's multiplied by a to the power of 4 times 5, or a to the power of 20. And then lastly, I can do the multiplication step. We'll multiply these powers and add their exponents, which gives us a to the power of 26. Okay, I can do the same thing here, so I can do... So one thing about BEDMAS that is probably not drilled so heavily in, say, grade 7, 8, and 9 when you learn about BEDMAS is that the top of a fraction can be considered a bracket. It's like something you want to, if you can evaluate anything on the top or the bottom of a fraction, you should do that in the same way that you would evaluate things on the inside of a, inside of a bracket, like an F. So here, we're going to treat this as a bracket step. Okay, and so we're going to say we'll multiply those together first, and then we add their exponents, like that. And then we have a division step here, because b to the power 15 is being divided by b to the power 3, which means we subtract the exponents, and we get b to the power 12. Now we did this one in class. I'm going to do it here again just to explain the logic here. Again, we'll use BEDMAS. We have a bracket step here, so we'll do the bracket of c to the power 5. You can add those exponents together when we multiply. And then we have c cubed. So that's an explicit bracket, but as I was saying, we also want to tend to treat the top and the bottom of a fraction like brackets themselves. And one of the reasons for that is that really this is another way of saying I have this big fat bracket and I have c squared times c cubed. That's all squared. And it's all divided by this big fat bracket with inside it c cubed inside it. So we have these big fat brackets that kind of rule the roost here. And that's just another way of writing this fraction, because a fraction is really just a division idea. So that suffices to say, if we want to continue to try to evaluate anything on the top or the bottom of a fraction before we start letting them communicate with each other and treat them as a bracket step. So on the top here, I can see that I can evaluate this exponent step within that bracket, and so I should do that. That's a multiplication. It would be 5 times 2 would be c to the power of 10. And that's using our exponent rule of having powers to the power of something. And then the same here, we'll have c to the power of 9. And together that gives us, oh, and now we can do this division step. We can move on. We have 10 take away 9. Then we get c to the power of 1, which is another way of saying c. Okay. Next. As we said before, we want to treat the top and bottom of a bracket, of a fraction as a bracket. So we'll multiply the top together first. Not much we can do on the bottom. So it says, okay, so I could rewrite that, and I think I will. I'll say it's x cubed times x power 4 times x squared times y all over xy cubed. And I can change the order things are multiplied because it doesn't matter what order we multiply things in. So I could say that is x cubed times x squared times y to the power 4 times y. And it's all over x times y cubed. Now you may find you don't need to do this to think about this problem, and that's fine. This is just another way to think about it if you're having trouble with it. And then I can see, well, these have the same base, so I can multiply these together and add their exponents to get x to the power of 5. That's the same thing I can do here. I can add the exponents of 4 and, well, there's a little invisible 1 on that y. So I get y to the power of 5 as well. That's all over x times y cubed. And now we can do this division step. So I can divide x to the power of 5 by x to the power of 1. I subtract their exponents, I get x to the power of 4. And y to the power of 5, take away 3, so it'd be y to the power of 2. And the last question gets a little hairy, and you can expect the further you go in math, the more hairy the stuff tends to get, but also the more practice you had with it, and so it starts to really become a process where your pencil does most of the hard work for you. All right, so we should start on the top and bottom of the bracket and see if we can simplify anything there. I can see that I can actually square this entire expression. Okay, and we talked about how there's an exponent there, and we distribute the exponent to each of these on the inside. We multiply each of them. So x has 2 to the power of 2 times x to the power of 4 times 2, or x to the power of 8, times y to the power of 2 times 2 is 4. And that's all multiplied by 2 cubed times y cubed. And on the bottom I have 2y to the power of 4, and that's times 2 cubed times x to the power of 6. Okay, so there's lots going on here. I think I'm going to try to regroup them in the same way I did over here. So I could say it's 2 squared times 2 cubed. There's no x's to group on the top, so I'll just leave that as an x to the power of 8. And y to the power of 4 times y to the power of 3. And on the bottom, I get, I'll group the 2's together, so I get 2, and I'll just put a little 1 as an exponent just to remind myself it's raised to the power 1, and 2 cubed. And then I have x to the power of 6, and I like to go alphabetical order, even though the y was first. Nothing wrong with keeping it in the opposite order, of course. Okay, and I say, can I do any more simplification? And I can say I can group these together. I can say that's 2 to the power of 2 plus 3, 2 to the power of 5, which is 32, but I have a feeling keeping it as a power is going to be helpful to me later. I just have an intuition, so we'll see if I'm right or wrong. And I'm going to multiply these together, and I get 4 plus 3, so I get y to the power of 7. And on the bottom, again, I can add these exponents together to get 2 to the power of 4, x to the power of 6, and I have y to the power of 4. Now lastly, I can actually do some division here. I can divide 2 to the power of 5 by 2 to the power of 4, and we see that keeping these as powers did end up paying off. I don't have any complicated division to do anymore. I just have to subtract 4 from 5 and find that the top becomes 2 to the power of 1, which is another way of saying 2. And x squared, x to the power of 8, take away x to the power of 6, leaves us x to the power of 2. And x to the power of 7 divided by, y to the power of 7 divided by y to the power of 4 is y cubed. Okay, and that is all the questions on that worksheet. Let me know if you have any questions. Email me, or you can come see me during Flex.